Among the things that we can use derivatives for, we can use them to understand what's going on with the graph of a function. In particular, we can find where the graph of a function has a bump or a local maximum or a dip, also known as a local minimum, because those are places where tangent lines are horizontal. Now, let me get rid of these tangent lines, and I'm going to throw in some other little line segments. All right, I'm going to give you formal definitions in a little bit, but right now I'm going to say that f has a local maximum at b. The actual local maximum value is f of b. It's a y value. That's something to straighten out right now. A local maximum is a y value. And I'm making a big old point about that because people get this wrong every semester. The local maximum occurs at an x value, but the x value is just an input. The actual number is the y value. Sometimes people will even give me an ordered pair. They'll say the local maximum is bf of b, which doesn't make sense because that's not even a number, it's a point. So local maximum is a y value. We also can say here that f has a local minimum at c. The local minimum itself is f of c, again, a y value. Now, all that is meant by a local maximum and local minimum is that near b, there's no output that's bigger than f of b. You can see that in this picture here. That's for a local maximum. For a local minimum, near c, there's no output that is smaller than f of c. Intuitively, you understand this. But I said I would formalize this as a definition, and I will. A function f has a local maximum value at c if there is an open interval I containing c such that f of c is less than or equal to f of x for all x in the interval. Let me say what that means here. I know that said c, and here we're talking about b. I'm sure you can handle that. And what we're saying here is that the function value f of b is a local maximum because I can identify an open interval around b, that's both sides of b, such that for all of those x values, the inputs are not bigger than f of b. The outputs for all of those inputs are not going to be bigger than f of b. Likewise, we can say that there exists an open interval around c such that for all of those inputs, there isn't an output that's smaller than f of c. So I can actually doctor up this definition here a little bit and say here, well, I'll just put minimum and then change the inequality. Notice the local maximum is f of c, or the local minimum is f of c. Again, I don't mean this c to be this c. This is just some function value, right? But the point here is it's an output value. It's a y value. Please get that down now. Now, you may have seen I have another graph here floating around, and it's a graph of g. This one is a parabola. And you can see that we have a local minimum at a. The local minimum value is g of a. But I have this graph here because g of a is the smallest output for the entire function. So here we can say that g has an absolute minimum at a. And then the absolute minimum value is g of a. We could formalize this. A function has an absolute maximum at c if f of c is bigger than or equal to f of x for all x in the domain of f. And then the absolute maximum is the y value f of c. And again, we can say the same thing about minimum by reversing the inequality. Notice that in our pictures here, g has no absolute maximum. It keeps going on forever. It has no local maximum either. F has neither an absolute maximum because it keeps going up to infinity, nor an absolute minimum because it keeps going down to negative infinity.